moving on to our second method of interest. So smooth particle hydrodynamics, or SPH, is a meshless Lagrangian computational approach. Now, this technique is much different to traditional CFD because it doesn't actually require a conventional mesh or a fixed grid, and nor does it rely on empirical models to compute the liquid and solid phases or their interactions as before. So to put it simply, with SPH, the fluid is defined by a finite set of interpolation points. Each computational point or particle or element, as we call them, has an associated mass, momentum, and energy. The movement of each particle will result from the integration of Newton's second law, subjected, of course, to the forces that are imposed on that particular particle. Now, these forces can result from pressure gradients, viscous forces, or other body forces acting on that element. And importantly, a property within the flow, such as density or velocity, is obtained by using an averaging or a smoothing algorithm that integrates over the neighboring particles. Now, initially, the SPH algorithm does sound quite similar actually to the DEM algorithm, because essentially the momentum equations for every SPH particle or element are integrated numerically based on the forces applied by the neighboring particles, which is similar to the concept of contact forces in DEM, right? Now, the major difference, though, between SPH and DEM is that the interparticle forces in SPH are basically derived from the Navier-Stokes equations instead of particle interaction laws or contact formulations. There's also, of course, the concept of interpolating field data, which doesn't happen in DEM. Now, with this method, because we are tracking particles within their reference frame, it's a Lagrangian approach, pure advection is treated exactly. And so for this reason, SPH is particularly suited for large displacement type problems for both fluids and solid materials, as well as for modeling of flows with distinct free surfaces. And so another benefit of the approach is that the actual computations that are applied are executed only where the material actually is. And so as you could imagine, this is particularly useful for problems with splashing in the context of fluid flows. Now, practically, what can we use this method for? We'll take a look at this as we progress through the next set of slides, of course. But as we can see on screen, the method is typically or commonly used for car weighting analysis. So obviously a splashing free surface type of problem. We can also extract dipping time in the bottom right of the screen or other wetting parameters, which are of course relevant for the car weighting analysis again. Sieving type of applications are also applicable with this method, as well as, of course, a coupling with DEM, which we'll dive into shortly, as you can see in that video there, looking at a SAG mill. Now, I'm just going to go into a little bit more detail, but I'll keep things high level. But basically, the core concept of SPH is to approximate the properties of a fluid by dividing it into that set of finite discrete elements or particles. Now, intuitively, you can think of each particle or element as small pieces of fluid which will interact with their neighbors through pressure and viscous forces. Each particle will contain and carry properties of that fluid, such as density, pressure, velocity, and the value of any physical quantity at any point in the fluid is interpolated from the properties of these particles and their spatial distribution. It's a function of their neighbors. And so each of the fluid particles, well, if we're considering one particle at position A, will interact to varying degrees with its neighbors at position B. based on the separation distance between particles or elements and the value of the smoothing or the kernel function, as we call it. Now here, the integral interpolant of any field variable A is computed by a summation over the neighboring SPH particles, considering mass, density, and position. Here you can actually look at the ratio of mass over density as the volume associated with the fluid particle. And of course, the gradients of any given field variable are computed in terms of the gradients of the kernel function. Now for the SPH DEM coupling, how we couple these fluid elements to solid objects, essentially Rocky uses a resolved method for fluid particle interactions. It doesn't rely on any sort of closure models for the fluid particle momentum or the heat transfer coupling. Instead, the coupling of these two models is executed through basically a solid fluid no-slip boundary condition. So importantly, the method requires that the solid particles are sufficiently larger than the SPH elements or the mean interparticle spacing for the SPH elements. Now, the interaction is firstly achieved by placing SPH particles in the interior of the DEM particles. These interior or these linked particles will move and rotate with the parent DEM particle and will have an associated mass, density, and velocity. These properties are adjusted to satisfy the no-slip condition. To do this, essentially the fluid velocity at the surface of the solid or the linked DEM particle needs to match that of the solid velocity. So let's just summarize this really quickly. Let's summarize the pros and cons of SPH over CFD really quickly. It essentially just boils down to a few factors. Given that the SPH algorithm is very similar to DEM, as you could expect, it's very easy to parallelize, meaning that it's very efficient on the GPU, offering significant speed up over traditional CPU-based solvers. The fact that particles are tracked exactly means that free surfaces can be resolved with ease. There's not going to be any diffusion errors. And because it is a meshless approach, the model setup is extremely easy and complex geometries can be handled with ease because we don't have to spend time and resources at the geometry preparation stage like with traditional finite volume methods where we have to end up with a really clean geometry.